Okay, so let's dive right in. We all know modern crypto is built on a simple asymmetry, right?
Right, multiplying two huge prime numbers is easy.
But trying to go backwards, factoring that result, is supposed to be almost impossible.
Exactly. But the sources we looked at propose a really wild idea. What if you just stop doing math to solve it?
I love that. So you take the integer factorization problem, the IFP, and you don't treat it as an algebra problem anymore.
Not at all. You reframe it completely. It becomes this colossal logic puzzle, a Boolean Satisfiability Problem, or SAT.
You're literally building what you could call a factorization machine.
That's a great way to put it. You're swapping the equation $1 equals a p times q tail for a digital circuit.
So the unknown primes, p and q, they become the input switches.
Uh-huh. And the number you're trying to factor, n, that's the fixed output. It's like the lights in the machine are already lit up.
And the SAT solver's only job is to figure out which switches you need to flip to make those specific lights turn on.
Precisely. And to do that, you first have to translate the entire circuit into this massive logical rulebook.
Which is called conjunctive normal form, or CNF.
Right. And the scale here is just, immense. The circuit itself, with its grid of bitwise products and this spiderweb of adders, it scales quadratically.
Okay, so a theta into complexity, that sounds like it should just explode. How do you even begin to manage that many rules?
Well, that's where this really clever technique comes in, the Satan transformation.
Right.
Instead of one massive, impossibly complex rule for the whole machine, you just create tiny local rules.
For every single component.
For every wire, every single gate. You give each one its own variable. And that's the magic. It means the number of rules, the clauses, it only grows linearly with the size of the circuit.
So it stays at that manageable theta into complexity. It doesn't become exponential.
Exactly.
And this is where, for me, it got really interesting. The sources dive into these incredible optimizations, like the 18 clause, full adder.
Yes.
Why is that so important? I mean, it's just adding 2 bits.
Because it's all about language. A standard logical breakdown for an adder might take, say, 82 clauses. It's clunky.
Okay.
Shrinking it to just 18 is like teaching the solver a hyper-efficient dialect for arithmetic. It slashes the overhead.
But even with that, that genius-level optimization, pure SAT solvers still hit a wall with crypto-sized numbers.
You do. They fail.
Where does it all break down?
It's the carry chains. That adder spiderweb. Think about it. In arithmetic, changing one bit at the very beginning can change every single bit that follows.
The avalanche effect.
That's it. It's a global property. And a SAT solver is built to think locally.
Yeah.
It's just structurally blind to the deep algebraic nature of what it's doing.
So the very thing that makes arithmetic work, carrying a 1, is what defeats the logical machine.
That's the irony, isn't it? Which brings us to the hybrid approach that researchers like Curtis Bright and Yamin Ajani pioneered.
The SAT-CS model.
The perfect synergy. You let the SAT solver do what it's good at.
The combinatorial part. Just guessing variables, trying combinations.
Yes, handling the logical chaos. But then you bring in a computer algebra system, a CAS, to act as this powerful number theory oracle.
So the SAT solver makes a guess, and the CAS, which actually understands math, checks it using real algebraic rules.
Instantly. The CAS uses these really advanced lattice reduction techniques, like Coppersmith's method.
And those are especially good for leaked bit problems.
Incredibly good, especially when the bits are scattered all over the place, which is what you often get from, say, a noisy side channel attack.
So a pure SAT solver couldn't handle that, and pure algebra would struggle with the scattered data.
But together they can solve problems that were considered completely out of reach.
So when you step back, the big takeaway here isn't just about the sheer volume of logic. It's about translation.
It's entirely about translation.
Yeah.
The difficulty is enforcing a system that thinks in logic to understand the structure of arithmetic.
And the success of this hybrid system shows that how you represent a problem fundamentally changes whether you can solve it.
That's the provocative thought, isn't it? If we can crack parts of a hard arithmetic problem by translating it into logic, what other intractable problems out there are just waiting for the right translation?
What other formal languages could we use to unlock things we currently see as impossible?
Exactly. What else could we solve?